Hello everybody, this is Dr. Bricker here with a review for Exam 2 for Physics 220. So the exam is over Chapter 5, and then we went up to Chapter 9 and 10. So no Chapter 6 on this one. That's the most recent material we've covered, circular motion, but it's not on this test. Going along with that would be homeworks 4, 5, and 6. I mention that because if I were to study for this test, I would definitely go over this review, which you're doing now, look at homework 4, 5, and 6, go back over the PowerPoints that we've done that, and then also read the chapters. And if you don't have time to entirely reread the chapters, at least look at the summaries at the end of the chapters. They're pretty good. Okay, so what I want to do is just go over the practice test and give you some hints along the way for what to study. Okay, let's take a look at it. Okay, so here's the first question. Again, just like the first test and like the practice test, it's multiple choice, but you do have to show your work. So no work, no points. Two air track carts move along an air track towards each other. Cart A has a mass of 450 grams. It moves to the right with a speed of 0.850. Cart B, 300 grams, moves towards the left. Okay, so be careful. Moving towards the left, this is going to be a collision. Moving towards the left means that the velocity is negative. You'll have to insert that. Left means negative in this case. What is the total momentum of the two cart system? Okay, so one cart's moving one direction, one's moving the other direction. What is the total momentum of the system? So this is a Chapter 9 question. So let's take a look at this. Okay, so here's the picture I have. Here's mass A moving to the right. Here's mass B moving to the left. We want to know the net momentum. So remember, momentum in general is mass times velocity. So this one over here would be 0.45 kilograms times 0.85. This is to the right. This one's momentum. Maybe I'll call that A actually. And this one is same thing, mass times velocity. So we've got 0.3 kilograms and then 1.12 meters per second. And notice I put this into kilograms. Okay, so let's actually multiply this together. 5 meters per second. Let's multiply this together and see what we actually have. Okay, so we've got the first one, 0.45 times 0.85. So 0.3825, that is to the right. And then the other one, 0.3 times 1.12. I'm just looking at this. I mean, technically, this is negative, but I know it's to the left, so I didn't write the negative sign down. You can if you want to. That would be perfectly fine. Well, let's do it that way, and I'll show you what I'm talking about. So this would be negative 0.336 kilogram meters per second. Same thing over here. Okay, so when you add these together, you'll have 0.3825 plus a negative, so I'll just do minus 0.336, 0.0465. The fact that it came out positive means it's moving to the right. Kilogram meters per second. Let's see if that's one of the answers. Okay, and it is. It's to the right, this amount. Okay, so the takeaway from this one is, make sure when you're doing these with momentum, you have to know right and left. You can't just take the magnitudes and add them together. Momentum is a vector quantity. Okay, let's look at the next one. A girl throws a ball of mass 0.8 kilograms against the wall. The ball strikes the wall horizontally. Okay, so it's moving horizontally with the speed of 25 meters per second. Bounces back with the same speed. The ball is in contact with the wall for 0.05 seconds. What's the magnitude of the average force exerted on the ball by the wall? All right, let's take a look at this one. Okay, so here's what I have. Mass is 0.8, initial velocity 25, going this way, hits the wall, bounces back with the same magnitude, but in the opposite direction. Again, the key thing is, then that would be minus 25. Time of 0.05 seconds, how much is the force? So here's a clue. We've got a problem with mass, velocity, force, and time. The impulse relationship should jump into your head. So impulse means change in momentum. Let me write it like this so it looks cleaner. Impulse, F times time, change in momentum, final momentum minus initial momentum, and it keeps going. mv final minus mv initial. So the hint here is mass, velocity, force, time. Let's use the impulse relationship. Now you could very well try to figure out the acceleration from the speeds here, the velocities really, and the time. You can get the acceleration, and then from Newton's second law you could use F is equal to ma to figure out the force, because you know the mass. But we can just do this in one step with the impulse relationship. So force times time, mv final minus mv initial. And then what I'm looking for is the force. The only thing that I don't know is the time. By the way, let me back up a step. This whole part over here that I set up the problem, I wrote down what I know. Here's a picture. Here's what I'm looking for. Right away, that's 4 out of 10 points. You know, and organizing your thoughts like that to solve this problem. Okay, and then once you put in this impulse relationship, you know, force times time. That's really what this part is. Force times time, mv final minus mv initial. I'm just using this part of it. Actually, oh, sorry. This was part of the line before that. Okay. Final minus initial, mv final minus mv initial. Here's where I actually started the problem. Okay. Good. So once I put this part down, now I've got 6 out of 10, and then the rest is figuring out how to actually solve this. So the force, then mv final minus mv initial divided by the time. When you put in the numbers, this will come out to be negative. That's okay. It just means the force is this direction. And the answer just wants the magnitude of the force. Okay, so I'll leave that to you to put this in. Okay, very good. Let's take a look at the next one. Okay, so we just completed this one. You'll see a similar problem. By the way, when I make the actual test out, I use the practice test as sort of a template, and then I find similar problems to that. Okay, so you'll definitely see something involving the impulse relationship. Okay, you'll see a similar one to this. Well, let's work out this one, and then I can say a little bit more about that. A push of magnitude P acts on the box of weight W, as you see in this picture. The push is directed at an angle below the horizontal. Okay, you see that here. The frictional force on the box due to the floor is equal to, so the frictional force has to be equal to one of those. Please draw the free body diagram and solve this. Okay, so let's do that and solve it. Okay, so here's what we have. Let's draw the free body diagram. We're always going to have the weight here. Now we have this force P at some kind of angle. I'm going to draw it down here. It doesn't really matter where exactly, but I like it to be going from the dot here. So this is theta. And then we also have a normal force this way. And they're implying that there's friction because they're asking us to solve for friction. So which way is the friction? Well, this force P here must have a force in the x direction and a force in the y direction. Okay, so if we were to balance horizontal forces, we know that if you have a component of P this way, friction's got to be back that way. And then I also know that P in the x is equal to friction. So that's what friction's equal to. It's just that's not one of the answers in this form. So let's take a look at this triangle. Maybe we can do something with this. Well, it looks like the cosine of theta, so from this triangle, the cosine of theta, that's the adjacent side, is px over p. So then p cosine theta is equal to px. And I could take that and plug it in here, and then I have the answer in the same form. So p cosine theta is equal to friction. Okay, so for the actual test, you'll see a very similar situation. I'm not going to ask you the same thing. Here's a hint. Make sure you know what the normal force is equal to. Okay, usually it's just the weight, but it's a little more than that with this problem. So think about it and try to solve that one. All right, let's look at the next one. Okay, number 4. Which one has a larger kinetic energy? 50 kilogram object moving at 4,000 meters per second, or a 1,000 kilogram object moving at 20 meters per second. Well, a quick analysis of the numbers shows that it has the same momentum, right? Momentum is mass times velocity. So 50 times 4,000 is the same thing as 1,000 times 20. That doesn't mean they have the same kinetic energy, though. So let's actually solve for the kinetic energy. So don't fall into that trap of if they've got the same momentum, they have the same kinetic energy, because they don't. All right, let's solve this one. Okay, so as you know, kinetic energy is 1/2 mv squared. So here's the first one, 1/2 50 and then 4,000 squared. See, the speed here is squared, so this is going to be a really big number. Let's take a look at that. So 1/2, 0.5 in other words, times 50 times 4,000, and then don't forget to square it. So something really, really big. 1, 2, 3, 4, 5, 6, 7, 8. 4 times 10 to the 8th. And this is kilogram meter per second squared. That's a Newton times another meter, so this is in joules. And then we can look at the other one. 0.5 times 1,000 times 20 squared, or in other words 400. So this is a lot less. 1, 2, 3, 4, 5. 2 times 10 to the 5th joules. So definitely the lighter one traveling faster has more kinetic energy than the more massive one traveling slower. So just put the numbers in and see which one is greater. You'll have something similar to that on the practice or on the actual test. All right, let's go on to the next one. All right, a stone can slide down one of 3 different frictionless ramps as shown. For which ramp will the speed of the ball be the greatest at the bottom? So in class we did several different voting ones like this. So if you remember, the path doesn't matter. You're up here at a certain height, regardless of which path you take. When you're down here, you're on the ground. So each of these has the same gravitational potential energy to begin with. So that gravitational potential energy is turning into kinetic energy at the bottom. That was just like the lab that you just did too. So they're going to have the same speed at the bottom. Now if I was going to explain it, I would do it like this. Let's take a look at that. Okay, so I would say that we're taking gravitational potential energy and converting it into kinetic energy. So gravitational potential energy is mgy. This is 1/2 mv squared. The mass doesn't matter. You can see the mass actually cancels out. So the speed at the bottom is going to be, multiply both sides by 2. 2gy is v squared, and then take the square root of both sides. Okay, so and then you can say same y means same v at the bottom. So I did this with formulas. You could very well just do this with words. You could just say the gravitational potential energy is the same for each of them at the top, depending on it's path independent, same gravitational potential energy. That's turning into kinetic energy. Same height, mass doesn't come into play, so they're going to have the same speed at the bottom. Okay, so you'll see something similar to that. On to the next one. Okay, number 6. A 1,000 kilogram whale swims horizontally to the right at 6 meters per second. It suddenly collides. As soon as you hear that word collides, you know it's got to be a conservation of momentum problem. Collides with a stationary seal of mass 200 kilograms. The seal grabs onto the whale and holds on. What is the speed of the two creatures just after the collision? You can neglect any drag effects of the water during the collision. Okay, so this is like the lab that we did. Although we didn't have a whale and a seal, we had a couple of carts. All right, let's take a look at it. Okay, so hopefully if we have this sort of whale versus seal problem, you can draw it a little bit better than I did, but here's the idea. The whale is moving, the seal is stationary, so this is before the collision, and afterwards the whale grabs onto the seal, and then they swim off together. So the initial momentum of the system is equal to the final momentum of the system. This is something we call a perfectly inelastic collision. It's the sticks together type of collision. So with collision problems, you look at the momentum before the collision and then the momentum after the collision. So the mass of the whale was 1,000, the seal 200. The whale is actually moving, the seal stationary. What's their combined final speed? So you can imagine it's got to be less than 6, right? Because now the mass of the system, the mass, really, you can think of it like this, of the seal has increased because this whale is holding on to the seal. I guess I should say the mass of the whale has increased because the whale is holding on to the seal. Okay, let's actually set it up then. Initial momentum is equal to final momentum. That's the key for this problem. Now the initial momentum, it's the mass of the whale and times the velocity of the whale initial. Oops, I called that mass. I meant to call that speed. Same thing here, so correct that. Okay, velocity of whale initial. Velocity of seal initial. Okay, so again, back to this side, mass of the whale and then velocity of the whale initial. Now the seal doesn't have any momentum initially, so I didn't even write it down. And then afterwards, we have mass of the whale plus mass of the seal. That's because it's the stick together equation, or collision I should say, and then times their common final speed. So you could, if you wanted to, figure out the initial momentum of the system, right? That would be 1,000 times 6. So the initial momentum of the system is 6,000. It's got to be equal to the final momentum of the system. And the final momentum is now contained in both of the creatures here. Okay, so let's do another step of algebra. Mass of whale, velocity of whale initial, divided by the total mass. That gives you the common final speed. Okay, so we've got 1,000 kilograms times 6 meters per second divided by 1,200 kilograms, right? This is 1,000 plus 200. Okay, so it looks like we end up with 5/6 of 6, which is 5. Okay, so their common final speed then would be 5. All right, let's look at the next one. By the way, we're halfway over. Hopefully that doesn't seem too bad to you. Okay, 328 kilogram car moving at 19.1 in the plus X direction. Okay, good. Hits from behind a second car moving at 13. Okay, so the second car is not going as fast in the same direction. If the second car has a mass of 790 kilograms and a speed of 15.1 right after the collision, what is the velocity of the first car after the sudden collision? So picture it happening. Faster car comes up from, hits a slower moving car. The slower moving car actually then speeds up, you know, in this scenario. And we want to know what is the velocity of the first car after this collision, right? Because the second car goes from 13 to 15.1. You could imagine that happening. If that happens, the first car is going to have to actually slow down to conserve momentum. Good, so let's set it up. It's a collision problem. Again, collisions, we use conservation of momentum to solve these. Let's look at this. Okay, so here's mass 1 moving to the right with velocity 1 initial, which is 19.1. Mass 2, which we know, is initially moving at 13, also to the right, but this one's going faster than that one. They collide. So this is the initial situation before the collision. And then after the collision, we know that mass 2 increases to 15.1. We want to know what happens to the speed of the first one. Okay, so a collision again. Initial momentum is equal to final momentum. So we have mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, is equal to mass 1, velocity 1 final, plus mass 2, velocity 2 final. So by, again, writing this down, having a picture, that's going to be 4 out of 10 points. Once I write this down, now I'm up to 6 out of 10. And then I've got to put the details in. So before the collision, each of them is moving. Here's the momentum of the first one, momentum of the second car, and then afterwards, momentum of first, momentum of second. And then it just becomes an algebra problem. you know everything except V1 final. You know everything except for this. So you have to do a little bit of algebra and then solve for that. Maybe I'll do one more step here. Mass 1, velocity 1 initial, plus mass 2, velocity 2 initial. And then I'll subtract this. I'm putting everything other than what I'm looking for on one side of the equation. Minus mass 2, velocity 2 final is equal to mass 1, velocity 1 final. And then divide both sides by mass 1, just to save a little bit of time. Divide this side by mass 1, divide this whole side by mass 1. Okay, and then you can put the numbers in and solve for it. Okay, excellent. So you'll definitely see a collision like this. Now notice the form of this is different. These didn't stick together after the collision. So I don't have like mass 1 plus mass 2 times some kind of common final speed right here. Right? I don't have that because they're not stuck together. Okay, let's look at the next one. Okay, number 8. This goes back to chapter 5, by the way. Two boxes, P and Q, you can see in the picture, P and Q, mind your P's and Q's, are on a perfectly smooth surface, are connected by a light horizontal cord. The mass of P is bigger than Q. A horizontal force F is applied to box Q, as you can see in the picture, accelerating the boxes to the right. Okay, so if they're accelerating, that means there's a net force. The magnitude of the force exerted by the cord on P, the magnitude of the force exerted by the connecting cord on body P is. Okay, so we want to know how much this is. Oh, in comparison to, let me read it one more time. The magnitude of the force exerted by the connecting cord on body P is, okay, 0, greater than F, less than F, or equal to F. Yeah, sometimes you've got to read these a few times. So we want to know if this, the magnitude of the force exerted by the connecting cord on P. So this tension here, is it 0? Is it greater than this force? Is it less than F but not 0? Or is it equal to F? Okay, let's take a look at this. It's a little tricky. We'll have to come up with some free body diagrams and figure out what these, which one's bigger than the other one. Okay, let's draw this out. Okay, so I've constructed the free body diagram for each of them. Here's P's. Normal from the ground on P, weight on P. I call this one tension on P. This is what we're trying to look at, the tension on P. That's what I'm calling it, in comparison to F. Now, here's the free body diagram for Q. Normal on Q from the ground, weight on Q from the earth. Here's that outside force, F. So if Q wasn't connected to P, we would have a greater acceleration. Because Q is connected to P, you know, what makes that acceleration not as great? Well, it's really this the tension, because there's a cord here. By Newton's third law, this tension and this tension are the same thing. So if I were to use Newton's second law then, so this is free body diagrams, I know this is equal to this because of Newton's third law. Let me use Newton's second law for this mass. The net force, ma, and it's mass Q times A, is going to be equal to F minus TP. This is the part that you have to supply. Remember, with Newton's second law, net force ma, and then you put the actual forces in. They call this generic F minus TP. So mass Q times A plus TP is equal to F. That means that F has got to be greater than this, right? If it wasn't greater, there would be no acceleration. So this this force here must be greater than that force moving to the left, or it wouldn't accelerate. So this answers the question. It's got to be greater than that. It's not equal to 0, though. If TP were 0, then this would not be accelerating, but it is. So to answer the question, this is bigger than TP, but TP cannot be 0. Okay? Excellent. So this, to me, is one of the harder questions on the whole test. So what we did was just look at free body diagrams and try to figure out how those forces are related to each other. You can't really just guess. You've got to come up with some way of justifying your answer. Okay? Let's look at the next one. Okay, so that's choice B here, less than F but non-zero. Okay, number 9. The coefficient of static and kinetic friction between a 3 kilogram box and a horizontal desktop are 0.4 and 0.3. So this goes back to chapter 5. What is the force of friction on the box when a 6 Newton horizontal force is applied to the box? Okay, so you'll definitely see a problem like this. Let's take a look at it. Okay, so here's what we know in the problem. I've written it down here. This is the free body diagram. Normal, weight, some kind of applied force. I'll just call it F app. That's the 6 newtons. We want to know how much is friction back this way. Well, the thing is, we don't know if we have static friction, and we don't know if we have kinetic friction at this point. Let's figure out the maximum amount of static friction. So this is the kind of problem. You're trying to move this box. You apply a force, you can't move it. You apply a bigger force, you still can't move it. So that implies that friction has increased. Remember, static friction does that, just like the lab that we did, the Newton's second law lab. You pushed on the crate bigger and bigger and bigger and bigger. It was a FET lab, if you remember. And finally, you broke it loose. So that whole time while you were applying a force, the force of static friction was getting larger until you finally broke it loose, and then you had kinetic friction. So let's look at the maximum amount of static friction and see how that compares to this applied force. So the maximum amount of static friction, Fs max, I'll do it right down here. The maximum amount, so static friction max, that's what I have written here. That's when it's equal to the normal force times mu sub s. Now in this problem, the normal force is equal to the weight. So this would be mg times mu sub s. Okay, so let's actually do this. M, so that's 3 times 9.8 times mu sub s. That was 0.4. Static friction is bigger than kinetic friction. 11.76 newtons. That's the maximum amount of static friction. Now we've only applied 6 newtons. So if we've only applied 6 newtons, friction only has to be as large as it needs to be. So right now, friction is only 6 newtons. So to answer this question, it's 6 newtons. If you apply 6 newtons, friction only has to be 6 newtons. Now if you were to apply 10 newtons, then static friction would be 10 newtons. If you apply something greater than 11.76, say for example you applied 15 newtons, well 15 newtons is bigger than the maximum that this could be. So in that, if that happens, it's moving. You have got kinetic friction. So whenever you are greater than this in terms of the applied force, then you're in the kinetic friction regime. And kinetic friction is the normal force times mu sub k. So the way to do these problems, if you remember, is to figure out the maximum amount of static friction, compare it to the applied force. If it's less than the applied force, then friction is equal to the applied force. Now if the applied force is greater than the maximum, then we've got kinetic friction, and you can solve for how much kinetic friction is. Okay. In this one, it's not larger than, the applied force is not larger than the maximum, so static friction just turns out to be equal to the applied force. A little tricky, so make sure you know how to do this kind of problem, because you'll see one on the test. I'm not saying this exact situation, but this concept. Okay, let's look at the next one. How large a net force is required to accelerate a 1,600 kilogram SUV from rest to 25 meters per second in a distance of 200 meters? Okay, so we've got mass, velocity, distance, and we're asking about force. So this is the work-energy relationship. You could do this by figuring out the acceleration, and then knowing the acceleration, get the net force that way. That's another way of doing it, but we'll use the work-energy theorem to solve this problem. Okay, let's take a look at it. Okay, so 1,600 kilogram SUV from 0 to 25 in this distance. How much is this force? Okay, so the work-energy theorem is FD cosine theta. That's the angle between F and D. I'm assuming they're lined up with each other, so the cosine of 0 is just 1, so I'm not going to write that. So the work, this is the work-energy theorem. I'm just giving it to you in general. FD, what does that give you? Change in kinetic energy. final kinetic energy minus initial kinetic energy. 1/2 mv final squared minus 1/2 mv initial squared. And then, again, a clue to if you should you use this or not is problems involving force, displacement. That doesn't look very good. Force, displacement, mass, and velocity. I called it x here, but it's the same thing. It's how far we've moved. So a clue is, given these inputs, I'm saying let's use the work energy theorem. That's a clue to use that. Okay, so I'll pick out this part of it. Force times distance, 1/2 mv final squared minus 1/2 mv initial squared. Now I just called it D because the book did. I'm just going to change it to my notation here. 1/2 mv final squared minus 1/2 mv initial squared. And we're starting from rest. So that term is 0. Okay, so I've got this I'm looking at. Divide both sides by x. And we're good to go on that one. Okay, everything's in SI units. You don't have to convert anything. So 1/2 1600 25 squared divided by 200. That'll give you the amount of force. So without putting numbers in, I'll leave that part to you. This is the way to solve it. Again, if you wanted to, you could figure out the acceleration from kinematics, final velocity, initial velocity, displacement. Figure out the acceleration that way, multiply it by m, and you would get the net force. Okay, let's look at the next one. See, we got a 1,500 kilogram car moving at 25 meters per second, hits a initially uncompressed spring, ideal spring, with the spring constant. What is the maximum distance the spring compresses? Okay, so we've got an energy conversion here. The only thing that we really have done with springs this semester is look at the spring potential energy. That's a clue that this is going to be a conservation of energy problem. So a car is moving. We know the mass and the speed it's moving. Hits an uncompressed spring. What's the maximum distance the spring compresses? So we're turning kinetic energy into spring potential energy. Let's solve this one. Okay, so kinetic energy becomes spring potential energy, and kinetic energy is 1/2 mv squared. Spring potential is 1/2 kx squared. So here's what I know: mass, speed, kinetic, spring constant. Remember, this is the reason I always call kinetic energy Ke, and K is just the spring constant. It's to avoid any kind of confusion. I mean, in the book, this is lowercase k. This would be bigger, uppercase K. But when you write it on a piece of paper, it's hard to tell. So I just use K for spring constant, Ke for kinetic energy. And then we're trying to figure out how much the spring is actually compressed. Okay, so here's what we know. Here's what we're looking for. Here's the idea that we're going to use, and then you can supply the details. The 1/2s actually cancel out. So mv squared over k is equal to x squared. Take the square root of both sides. And that will give you the amount that it's compressed. Okay, so I'll leave it to you to put the numbers in for that one, but that's the way to do it. Another energy conservation problem. Kinetic becoming spring potential. Okay, so you'll see some problem with spring potential energy on the test. Whenever you see a spring, it's going to be one of these energy conservation type problems. Okay, all right, on to the next one. Okay, actually, this is the very last one. The figure shows a famous roller coaster ride. You can ignore friction. Okay, that's good. The roller coaster leaves point Q from rest. So we're up here at point Q, initially at rest. What is the speed on top of the 25-meter peak? So this is actually kind of a complicated problem unless you use energy conservation, because as this cart rolls down this way, the normal force changes direction. It's very complicated. We're slowing back down. Trying to solve this problem with forces, you'd have to use calculus. You could do it, but it's tricky. We could solve this with energy conservation by looking at the total energy at Q, which is just made up of gravitational potential energy because it's at rest. They're just telling us it's at rest. It doesn't have to be at rest at Q, but they're telling us it is. And then this becomes at point S. I mean, here's the path that follows. We don't have to look at the whole path. We're just looking at where we started, where we end up. And where we end up at S, we have spring potential energy. No, we don't. We have gravitational potential energy and kinetic energy. thinking about the last problem still. So at S we have kinetic energy and gravitational potential energy. At Q we only have gravitational potential energy. Okay, so that's the idea behind the problem. Let's put pen to paper and solve this one. Okay, so you have your picture in mind. So the total energy at Q is equal to the total energy at S. Maybe I'll call this actually mechanical energy. That's what we called it in the lab. It's the same thing, right? Mechanical energy is made up of kinetic energy and gravitational potential energy. Okay, so again at Q, we only had gravitational potential energy. It wasn't moving. Now, if it were moving at Q, you'd have kinetic energy, but it's not. So we don't have to worry about that. And then at position S, we've got gravitational potential energy, and we also have kinetic energy. Now, the mass was not given, so don't let that dissuade you from doing the problem. Remember, if anything's ever going to cancel out, it's going to be the mass, and it turns out it's going to in this problem. Okay, so again, energy at Q, just gravitational, energy at S, both gravitational and kinetic. And then put some details in. Here's gravitational potential energy, mgy, and I just put Q here. That was 50 meters. And then that's equal to mgys, and that was the 25 meters. And then 1/2 mvq squared. So in the chapter, this is from chapter 10, you're not going to find the speed at Q formula. We have to use the concept, put in the details, and then hopefully what we're looking for comes out in the equation. And it will, and you can see that it does. This is what we're trying to find. There's a mass in every term, so the mass cancels out. To just a little bit of algebra here, and you can solve for Q. So put this to the left-hand side. I'll just do one more step. G times YQ minus G times YS is 1/2 VQ squared. Then, of course, you got to multiply both sides by 2, take the square root, and you get the velocity at S. Whoops, this is supposed to be at S. Okay, S. Right, this the higher position was Q. This is S. Okay, so make a note of that. I accidentally wrote Q when I meant S. Same thing here. This was the velocity at S, the lower height. Okay, excellent. So any questions, email me. Again, what I would do is go through this practice test, pretend like you're actually taking it as a test, see how you feel about it. Go back through the homeworks, the notes, things like that. Okay, and then you make your own formula sheet. Remember, your own formula sheet, both sides, put whatever you want on there. Okay? If I don't hear from you, I'll see you on Wednesday. Okay, bye-bye.